Today's video is about magnetism. In order to understand magnetism, we must talk about permanent magnets. Permanent magnets were found in central Greece in a place called Magnetism or something like that. And Greek said that permanent magnets were mineral components that were aligning to the North Pole or the South Pole, and they attract or they repel between them. So now in actuality we know that permanent magnet is given by the definition of its magnetic North Pole and its South Pole, and this happens when you left the permanent magnet to float. Let's say you put it in water, it would naturally align with the North Pole of the Earth's magnetic field, and so that would be a permanent magnet. If we would divide a permanent magnet by its half, we would obtain two new permanent magnets. So the next important thing to know is magnetic force. Magnetic force is only applied when the particle is in movement, and it is obtained by the formula that it's the charge times the velocity times the cross product of the magnetic field. And if we wanted to know the magnitude of the magnetic force, it would be given by the magnitude of the charge times the velocity times the magnetic field times sine of theta, because that would be the direction of the vector. And if we wanted to do this in a perpendicular way, saying that the angle between the velocity and the magnetic field is 90 degrees, we would say that it would be the magnitude of the charge times the velocity times the magnetic field. And that's how we would obtain this if we would have like a perpendicular thing going on. Now, going on with work and electric force, we must have these two concepts clear. Saying that if the magnetic force and the velocity are perpendicular, the point product would be equal to 0. So as the acceleration, the point product of the velocity would be equal to 0. Saying so that the kinetic energy, that it's given by mv square, so half, would be equal to 0. With this in mind, we can say that there is no work done to the particle. That's sad. So magnetic field units are the Teslas, which are given by the newtons times the second over the coulomb times the meter, the distance between the interaction. Or it can be also newtons over ampere times the meters. Okay, so motion of charged particles in magnetic fields. Using centripetal force, that is given by F equals to mv squared times the radius, since we have to know that the magnetic field induces a circular movement across the current or what's going on, and equaling this to what we saw in that whiteboard, we would say that the velocity times the magnetic field times the magnitude of the charge is equal to the centripetal force, since it is pushing the particle to move in circle, the magnetic field. So we would say that if we wanted to know the magnetic field going on in a radius matter, we would say that would be P over the magnitude of the charge. going on with magnetic force and a wire carrying current, with what we have seen in the other videos and in other units, we can easily say that this would be the current times the length of the wire times the magnetic field times the sine of theta. That would be the orientation between these two components. Or if we wanted to find it in a vectorial component way, we would say that would be L, the cross product of L times the magnetic field. This is how we would obtain the magnetic force on a wire carrying current. So another important topic is torque in a current circuit. This would be a overview of what is going on in a coil. Well, this would be a loop, simple loop. And we can see that it has two kind of different magnetic forces being applied, but they are the same, just that one is going downwards and the other one is going upwards. We have the unit vector and we have the length, that would be A. Making some, well, getting with some formulas, we would at the end obtain that the torque of just this simple loop and at the very half would be the current times the area times the magnetic field times the sine of the angle. But if we would substitute this loop by a coil, we would need to multiply the torque that is going on in a simple loop times the number of lengths that the coil has. And we have to remember that a coil is many loops going around. So this would be its torque. So I'm gonna erase this whiteboard so we can see magnetic dipole moment. So magnetic dipole moment is given by the letter mu, that is equal to the number of turns times the current times the area. And if we wanted to find the torque going on in the direction of the unit vector, we would say that the torque would be equal to the magnetic dipole moment times the magnetic field times sine of the angle. Saying so that at the end, if we wanted to find again the vectorial component, we would say that the torque would be equal to the magnetic dipole moment. We must clarify that it's the vector, the cross product of it with the magnetic field, and it's also vector. So another really important topic to talk about is Hall effect. So imagine we have a charged component and it's like a plate. So when the plate has some force acting on it, the electrons start moving to a side, most of them, and after a while many of them are in there, and we would say that in this side we would have a minus charge, and in this side we would have many of the protons that, as we know, they carry the positive charges, so we would have a positive charge in there, saying that this redistribution of the charges makes the electric field and the magnetic field at some point equal. So this is what we call the Hall effect. And this is really important since we sometimes need something to be divided as its positive component and its negative component. Another important thing that occurs when Hall effect is happening is a potential difference, the Hall's potential difference, that is given by the electric field times the distance, and we can clearly see that we don't really care about the magnetic field, although we can like just change it because they are equal, and we are caring about the distance that these two like sides have now. And we can also calculate the magnetic field with this potential difference that I just gave you. That would be BH times, and we now see a concept that we've seen in past videos, that is the drift velocity. So if we introduce this with current density, that we've also seen it, that it's the current times the area, over the area, it's equal to NBV. This is the drift velocity. Let me do it a little bit. So we would say that the magnetic field would be equal to the Hall's potential difference times the height. This is the height of the difference, times the number of electrons per volume unit times electron, over the current. This is how we would obtain the magnetic field using Hall's effect. Now we would solve an easy problem for this unit to end up with the video. So in the problem, they've told us that a charged particle has 20 microcoulombs of charge, and it is moving on the x-axis. This is the x-axis. See? So the particle is moving here happily, and then it is introduced of a magnetic field. Well, this would be the magnetic field. And we know that the magnetic field has its components that are clearly we know that this is Tesla's. So how can we obtain this easily? With a cross product, saying that the velocity, which they also gave us a velocity that is 50 meters per second, and well, having the cross product of these two vectors, we would know that 50 0 0, since we don't have any of them, this would be 0, 0.3, 0.7, so it would be I, the J, and the K. And this would give us a vector that would be 0 for the I, so if we would remember, having the charge, we would just multiply. Now that we have the cross product, we would multiply the charge times the cross product in order to have the magnetic force, and this would be given by 0 since we don't have anything to multiply, and 20 microcoulombs times 35 would give us minus 0.7 milli, and 20 times 15 would be equal to 0.3 milli. This would be newtons, and this would be all for the video. Thank you.